Let's do the Calculus Chapter 3 sample test. Find the critical points. Okay, let's do that. That means set the first derivative equal to 0. And the first derivative would be 3 down, which would cancel the 3, so it's going to be 2x squared. Bring the 2 down, that'll cancel 2, plus 3x minus 5, which happens to, I believe, factor 2x and x. And if I put 5 here, I get 5x, and if I put 1 there, that would multiply to be 5 if one of these is negative. And I'm going to get 2x and 5x. To get plus 3, it better be plus 5x and minus 2x. And I'm trying to get this critical value setting equal to 0, so x has to equal 1 or 2x plus 5 equal to 0. Subtract 5 divided by 2 equals negative 5 halves or negative 2.5. There's my critical points. And use the second derivative test. So I want you to actually do this. You got to show the test. So we got to take the second derivative of this. So f double prime of x would be 4x plus 3. And if I put 1 in there, I'll do that one first. If I put 1 in there, I get 4. So f double prime of 1 is going to be 4 plus 3. It's 7. I don't really need to know the number. I need to know that it's positive. Second derivative tells me curvature, so it means it's concaved up at 1, which means this has to be a min. Positive, so minimum. And f double prime of negative 2.5 times 4 is negative 10 plus 3. This is negative 10 plus 3 is negative 7, but I don't need to know that. I just need to know that it's negative, which means it's concave down, so it's a max. That's number 1. Find the absolute max and absolute min on the intervals from -1 to 1 for this. So I always want to check the endpoints. So what is f of -1? Well, I put -1 in here. I get 4 sine of -1 times pi over 2 is minus pi over 2 minus a -1 is +1, and that works out to be the sine of minus pi over 2. Minus pi over 2, the sine is -1 times 4. It's -4 plus 1, which is negative 3. I also need to find at the other endpoint at 1, which would make this be 4 sine of plus pi over 2 plus, and then I put in there -1, and sine of pi over 2 is 1 times 4. This would be 4 minus 1, which is plus 3. So far that's the largest so far, and that's the lowest, but we also have to check at critical values that are between -1 and 1. So I got to take the derivative to find critical values. And the derivative of 4 times something, it stays 4. Derivative of sine of something is the cosine of that something. Times the derivative of the inside, which is pi over 2. Minus the derivative of x is 1. So I'm trying to set this equal to 0. So I'm going to set for cosine of pi x over 2 times pi over 2 minus 1. So I'm going to add 1 to the other side, and it's going to be equal to 1. If I set this equal to 0 and add 1 to both sides, I get this. This is times the cosine, so I'm going to divide both sides. Okay, this first reduces to 2 pi, so I'm going to divide both sides by 2 pi, and I've got cosine of pi x over 2 equal to 1 over 2 pi. And so I need to take the cosine inverse of both sides. So the cosine inverse of 1 over 2 pi, and the cosine inverse of this would be pi x over 2. But this would only give me one answer. I have to think of all the possible ones. And so it might be better to go to the calculator and type this in. So I'm going to go to y equals, and I'm going to type in cosine of pi x divided by 2 and 1 divided by parenthesis 2 pi and I'm going to go graph, and I'm in this, let's do zoom 6, no, let's do zoom 4. And it looks like, I don't need that other thing in there. Oh, yes, I do. When are these equal? Graph. It happens there, 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 and there. Are any of those between -1 and 1? Well, that one looks like it's a little bit bigger than -1, and this one looks like it's a little smaller than -1. So we got to find that intersection point. Second, calculate the intersection point. And that's one curve, that's the other curve, and I want to get close to the answer, so I'm going to go move down to this one, and it says negative 0.898. Negative 0.898. And then the other place is going to be over here. Looks like it's going to be the same value, only positive, but I'll check that. Second, calculate the intersection. That's on that curve and near that place. And it says positive 0.898. And I have to find f at those places, just like I found f at these two places. So I probably should have just typed this into y equals. So I'll turn this one off and go down, turn that one off, and I'm going to come over here and just type 4 sine of pi x divided by 2, close parenthesis, minus x. And if I go to second table and delete, I can type in -1, and I should get -3. Type in 1, and I should get +3. Type in negative 0.898, and I get approximately negative 3.051, which is a little lower than that. And if I can put in positive 0.898, and I get positive 3.051-ish. So this is a little bit bigger than that. So there's my absolute max. and this is the absolute or global min. And these turn out to be neither. They're close, but not quite. Okay, number 3. Find the inflection points. That's where the curvature changes. So we have to get the curvature, which is the second derivative. This is a product. So the first derivative is going to be derivative of x times e to the x plus derivative of e to the x, which is e to the x times the first. And so that's the first derivative. Now if I do the second derivative, it's going to be the derivative of e to the x, which is e to the x, plus the derivative of x e to the x, which is what we just did. So it's going to be e to the x plus x e to the x, because this is the same as the original, so we get that, which is 2 of these e to the x's plus x e to the x, and we could factor out an e to the x times 2 plus x, and the only way the second derivative could equal 0 is if x equaled -2. So there's where the only inflection point happens, at -2 on the x. Now to know where it's curved up, well, we check before -2 and after -2 and see whether it's positive or negative. Curved up, it would have to be positive. So below -2, it changes at -2, the curvature changes. So we're going to try something above, like maybe 0. 2 plus 0 is 2, that's positive, and e to the 0 is 1, that's positive. And so over here, it's positive, so it's curved up on this side at above -2, and below -2, just to show you, I could do -3. 2 plus a -3 would be negative, and e to the -3 is still positive, because e to the x is always positive. So that would be negative, so it's curved down here. Changes at -2 from curved down to curved up. So determine the intervals where it is curved up. Well, it's on the interval from 2 to infinity. At 2, it's changing, so we do not include it. It just starts after 2, it's curved up. At 2, it's changing, and below 2, it'd be curved down. Page 2. So now we have match f if this is f prime. So this is telling me the slope is positive. So f has to be increasing, and increasing less later, but still increasing. So it's increasing and gets less increasing, so it's got to be concave down. And if you want, the second derivative would be the slope of this, which is a negative slope, which means it's concave down, but this is all above this line, so it's a positive slope concave down. So it's increasing and concave down, so this has to be D. Now this one, this is f prime again, and it's all positive, it's all above the line. So this function's increasing. It's increasing steeper because it's getting a higher slope, and then it gets the less slope. So f would have to look like going steeper and then less slope, but it's always going up. And so it's increasing and concaved up, and then concave down. And so that's E. No, that's decreasing. This is increasing, so it's F. Excuse me, F. Increasing, concaved up first, and then concave down. This one is all above the axis again, so this one's always increasing. So it's got to be an increasing, and it's got a small slope, and then it gets a higher slope. It's getting bigger, it's taller here, so it's getting a higher slope. So it's increasing slightly and then increasing more, which means it's got to be concaved up increasing. Increasing and concaved up. That's C. Draw a curve that has the following. Note the location of any cusp, but it has the following characteristic. Okay, so and then the tension is here to line these up with these places. So that was supposed to be at 3, and this is supposed to be at 5. It got a little off on the printer. So it has to be, first derivative is negative, which means it's decreasing and concaved up. Decreasing and concaved up. Now it's increasing and concaved up, so it would make sense to continue doing this, and I don't know how high it will go, but then what happens here? It has to decrease, but still be concaved up, which is going to force a cusp, because it's got to decrease, go from concaved up to concave down, increasing to decreasing, but always be concaved up, so I can't curve down. So there's got to be a cusp right here, decreasing and concaved up, and now it's increasing and concaved up, and then it's increasing and concaved down. Has to be a cusp there, and it can be something like this. And it could be at any height, but it's got to be concaved up, concaved up, concaved down. Decreasing, increasing. Decreasing, increasing, increasing, but concave down. Page 3. A rectangular sheet of metal is going to be made into an open top box with equivalent squares out of the corners. So, this is a problem we've done in class with different sizes, and it's a classic problem. We're taking squares out of the corners, and so we got to fold it right there, and fold it right there, fold it right there, and fold it right there, and these are gone, and they fold up to make a box. And we don't know how big the square's got to be, so we put X and X for all of them. You don't have to put them all there, but that's what the size of the square is, X by X squares. The sheet metal is 3 feet by 6 feet. And we want to make the maximum volume. So the volume of the box is length times width times height, which is the length is of the box. The sheet metal is 6 feet, but the bottom of the box is going to be just from there to there, which is going to be 6 minus an X, and minus an X is going to be 6 minus 2X. The width is going to be 3 minus X, or 3 minus 2X. And the height is going to be how much we fold up, which is going to be a height of X. And we got to take the derivative, so we can use the product rule, or we can multiply this together and then do just the regular power rules. So if I take X times this, I get 3X minus 2X squared. If I take and multiply these, 6 times this would be 18X. 6 times that would be minus 12X squared. And this times this would be minus 6x squared, and minus 2x times minus 2x squared is plus 4x cubed. These could be combined to be 18x squared. So, taking the derivative, v prime would be, derivative of 18x is 18. Derivative of negative 18x squared would be negative 36x. And the derivative of this would be plus 12x squared. It's a parabola, so we can use quadratic formula, we can graph. Some of you are don't understand when I say you can solve this by graphing. So I'm going to clear these out and go up here and just type in 18 minus 36x plus 12x squared. Let's just do zoom forward. Let's see if we see two answers. Yep, one place there and one place there. That makes us see 0. And we're trying to set the derivative equal to 0. So v prime equals 0 is our critical places, and we'll get second, calculate the 0 that's between 0 and 1, and I'm guessing 0.5, and it says no, it happens when x is equal to 0.634, and the other one would be there, which is between 2 and 3. Second, calculate the 0, 2, that's between 2 and 3. 2, enter, 3, enter, and my guess is 2.5, and it says, nope, x is equal to 2.366. Okay, and these would be x's, which are inches, feet. And now we have to look and say, is it reasonable to take half a foot, a little over half a foot out of each corner if it's 3 foot wide? And that's possible to do. Is it reasonable to take 2 1/3, over 2 1/4 feet? Well, 2 1/4 and 2 1/4 is way over 3 feet. This is not a possible answer. And if we went back to verify that, we can go back to the original equation and type in parentheses 6 minus 2x 3 minus 2x and x, graph, and it goes, the most you could do is 1.5, because that's half of 3, and the max is going to be up there at some value of there, so we're going to go second, calculate the max, that's between 0, enter, and 2, enter, and I'm going to guess at 1, enter, and it says no, it's at 0.6339, which is basically what we had. And the maximum there says determine the dimensions of the box that had the maximum volume. So that's the x that we have to take out. So the dimensions of the box are going to be 3 minus 2 of those. So we got, well, this remembers with the x. X, notice it's the same number. So we got to do 3 minus 2x. And so one dimension of the box this way is 1.73 feet by, this would be 6 minus 2x. And that's 4.73 feet by the height, which is going to be 0.63 feet. Doing it all in 2. So that's the dimensions of the box. Okay. 7. 500 feet of fencing to make 2 adjacent equivalent rectangle corrals. Determine the dimensions of the corrals if, and that should be just a small if, the area enclosed is maximized. So they're equivalent, so they're all the same. I'll just put X here. I can put Y for the whole thing, or I can put Y for here. Really doesn't matter. I'll put Y here for the whole thing. So the area of the whole thing to be maximized has got to be X, Y. And to maximize it, we take the derivative and set it equal to 0, get the critical values, but 2 variables. 500 meters of fencing. So we got to use 500 meters to do this side, that, and that. So X plus X plus X plus Y has to be 500. So now I can either solve for Y or solve for X. And so I'm going to just do, and it says the dimensions of each individual corral, X is on each one, so I'm going to use X. So I'm going to solve for Y to get the Y out of my equation. So I'm going to subtract 3X and divide by 2. And I'm going to put that in for Y. Which is 250x minus 1.5x squared. And I'm going to find the critical values by taking the derivative. Setting it equal to 0. So x would be 250 divided by 3 meters. And y would be 250 minus 1.5 times this. 250 minus 1.5 times 250 divided by 3, 125. But I want the area or the dimensions of a corral, so this would be half of y. Now if I set y to be here, then there would be 4y in this equation, and y would have come out to be half of that, which is 62.5 meters. So the dimensions of one corral is 250, if you like, is 83.33, 83 1/3, let's do it that way, meters by 62.5 meters. Okay. Last page. A spherical balloon is being inflated such that the radius is increasing by 1 centimeter per second. So dr dt is 1 centimeter per second. What is the rate of change in the surface area? So the surface area of a sphere is 4 pi r squared. And if we take the derivative of this, since there's only these two variables, we can take the derivative right away. And the change in the area with respect to time is 4 pi times 2r dr dt. So we've related dr dt to dA dt. There is an r. What is the rate of change in the surface area when the radius is 7? So we put 7 in for the r and figure out how fast the surface area is changing. So we got 4 pi times 2 times 7 centimeters times dr dt is 1 centimeter per second. And so I get 1 times 2 times 4 is 8 times 7 is 56. 8 times 7, 56. Is that right? Yeah, I think so. For some reason, I'm getting tired. It's late. 8 times 7. Just to make sure I did that right. Yeah, 56 pi centimeters squared per second, which is a reasonable unit for change in the surface area per time. And finally, a fighter jet is flying 800 miles per hour at an altitude of 5 miles. So here's my jet. Boy, I make such good-looking jets. And it's flying at 800 miles per hour and at a height of, the ground's down here, at 5 miles below it. It passes overhead of an observer, the observer down here, cute person there. At what rate is the angle of elevation changing when the plane is 13, so it's moving here, 13 miles from the observer? Angle of elevation. That's not this angle, but this angle. So the plane's going to be over here or over here. Doesn't matter which way you want to make it fly. I'm making it fly left to right. My little jet. It's still 5 miles high. So I have a triangle here. This is 5. This is changing, isn't it? It's how fast the plane is going. So I can call this x for the distance, and I get a relationship between the angle and these numbers. This is changing too, so this could be a y, but it doesn't ask us for that. It wants to know how this is working here. So I want to do x and 5 probably, so I'm going to say the tangent of the angle, because they want to know how that angle is changing, is 5 over x. Yeah? And so now I can take the derivative with respect to time. So the derivative of tangent theta is secant squared theta, but I'm doing it with respect to time, so I got to go times d, the derivative of the inside, chain rule, d theta dt equals, and this is 5x to the minus 1, so the derivative would be minus 5x to the minus 2 dx dt, derivative of the inside. So this direction is the x. The plane is going 800 miles per hour, so this is 800. The angle, let's see, we're going to have to figure that angle out. So we need to know how far it is if this is 13. So now we're doing it when this is 13. If this is 5, if you know your special triangles, this has to be 12, but you can also go 13 squared, which is 169, equals 5 squared, which is 25, plus what squared, and that happens to be 144, or 12 squared. 144 plus 125 is 169. So this happens to be 12 miles. Using Pythagorean theorem to figure that out for at this particular instant. We can't use this when we're setting up the relationship, but we can use it to figure it out for a particular time. This is always changing at 800, because that's how fast the plane is flying. And the secant is not the cosine, which would be 12 over 13, but it's 13 over 12 squared. So we got 13 divided by 12 squared d theta dt, which is what they wanted to know. At what rate is the angle of elevation changing? That's this. Equals minus 5 over x at this instant, so that's over 12 squared, or 144, times 800. So this is 169 over 144, so I'm going to multiply both sides by 144 over 169. 144 over 169. The 144s cancel. 169s cancel. And I get negative 5 times 800, which is negative 4,000 divided by 169. Negative 5 times 800 divided by 169 is negative 23.668 radians per hour. Because we're doing it in time is in hours, and all the other units, they're miles, but when you're talking about an angle, it's just going to be radians per hour. So that's how fast they're changing. The angle is, the change is negative because it's getting smaller. As this plane flies this way, the angle of elevation here is decreasing, following the plane. That's why we got a negative answer.